morning. Welcome to the class of Microwave Radar Engineering. The subject code is KEC 6074. This is lecture number 6 and we'll start with the waveguide. And now see, if I say in the last 5 lectures we have started with the transmission line. Now we will here discuss about the waveguides. And in the waveguide, as we know that in the waveguide, TEM mode will not exist. This we have already told in the last lectures, will not exist. Here TE mode and TM mode will exist. And waveguides are the metallic materials from which it is made up of. Just like waveguides are of two types: rectangular waveguides and cylindrical waveguides, or you can say that it is a circular waveguide. And in both the rectangular waveguide and cylindrical waveguide, both TE mode and TM mode will exist. Clear? Now, before we start with the rectangular waveguide and cylindrical waveguide, we will discuss or derive the generalized equation. Now see, EM waves are oscillation that propagate through space with the velocity of light. EM waves, as we know that they are transverse in nature. What is transverse? If I say transverse mode means the electric field or magnetic field components, magnetic field are perpendicular to the direction of propagation. Clear? Now see, if I say electric field and magnetic field both are perpendicular to the direction of propagation, that means they are not in the direction of propagation. That mode is known as the TEM mode, means in which EZ and HZ both are not equal to 0. And another way is in this TE mode, in this you can say the electric field will be perpendicular to the direction of propagation and electric field is not in the direction of propagation. And similarly for the TM mode, which is vice versa of TE mode. Now see, EM waves are transverse in nature. A plane transverse electromagnetic wave is defined as the wave in which both electric field and magnetic field vectors are at right angle to the direction of propagation. I have told you the transverse field is what? In which electric field and magnetic field are perpendicular to the direction of propagation. Now see, these are the Maxwell equation we have discussed in the EMFT subject. That is, first Maxwell equation is Ampere's law, that is del cross H equals to J plus B del D by del T. Second Maxwell equation is del cross E equals to minus of del B by del T, that is known as the Faraday's law. And third one is the del dot D equals to rho, and fourth one is the del dot B is equal to 0. D is what? Electric flux density. B represents your magnetic flux density, H represents your magnetic field intensity, E represents your electric field intensity. Now see, we will first find out the wave equation, solution of the for the wave equation, or you can say in the we have started from the for the basic of waveguides. We'll start with this wave equation. Now assume that if I say we assume that the all fields vary with respect to time, means the signal which is entered into they are vary with respect to the time. That means electric field E is equal to E naught equal j omega t, where E naught is what? Maximum value of electric field intensity. This is E naught, and omega is the frequency, that is 2 pi f, and f is your frequency of the wave. Now differentiate this equation with respect to t, that is del E by del t equals to will be equal to E naught equal j omega t multiply with j omega, and this is what? This represents your E. So that I can say that del E by del t equals to E into me j omega. Now see, what is j omega? J omega is what? We know that the j omega is what? With change in time, that is del by del t is equal to j omega. That I can say that you will see here, from here you can see that the del by del t is equal to j omega. Now again differentiate equation number 2 with respect to time, that is del square E equal to del t square, that is equal to j omega E naught j equal j omega t multiply में j omega. Now multiply these two, j omega multiply में j omega, that comes out to be minus of omega square equal multiply में E naught equal j omega t. Now this is equal to what? E. This is equal to what? E. Now see, just put this value del square E by del t square equal to minus of omega square E, and you will see that here del square E by del t square will be equal to minus of omega square. So I can define the operator del by del t is equal to minus of omega square, and del by del t is equal to j omega. Now consider the medium in which it is non-conductive, and that is conductivity is equal to rho equal to 0 and conductivity is equal to 0. Here we have taken the medium, that is air. Now from the first Maxwell equation we can define that del cross H equals to J plus del D by del T, and we know that the J equals to a sigma into E and D equal to epsilon into capital E. As we know that the medium is air, if I say the medium is air, that is sigma equal to 0, put the value here 0, that means del cross H will be equal to del by del T epsilon multiply में E. This epsilon is the permittivity. Now you just put this with del cross H, this is H vector, that is equal to epsilon into del by del T, and you know that this is what? Operator, that is equal to j omega. Therefore this is also one of the Maxwell equation, can be known as the Maxwell equation, del cross H equal to j omega epsilon into capital A. Now we'll use the Maxwell second Maxwell equation, that is del cross E is equal to minus of del B by del T. Now just put this B equal to what? Mu into me, just put the value, and this is equal to what? J omega. Now when you put this equal to j omega, you will see that del cross E is equal to minus of j omega mu into me H. Now we have to find the solution for the wave equation. Now you will see that here, taking the curl of the equation number 8, now you will see that this is equal, that will be equal to del cross of minus of j omega mu into mu H. minus j omega mu into m h, that comes out, that is del cross h. Put the value of del cross h from this equation, from equation number 7. On putting the value of del cross h from equation number 7, you will get del cross curl of E equals to omega square mu into me epsilon into me capital E. Now use the identity, that is del cross E is equal to, will be equal to what? Del dot E minus of del square E. Now put this value here in equation number this. On putting the value of equation, you will get this equation equal to omega square mu into me epsilon into me capital E. Now from third Maxwell equation, as I already told you, that the medium is what? Air, that is sigma equal to 0 and rho equal to 0. Now you will see that del dot D equals to 0, rho is 0, that means del dot T equals to 0. Therefore, put the value of D, I can say that del dot E will also be equal to 0. As we know that this component cannot be equal to 0, that means del dot E equal to 0. Now from equation number 9, del dot E equals to 0, put this value here 0, that is minus of del square E, that comes out to be, will be what? Put this value equal to 0. Now you will see that del dot E equals to 0. From the equation you will see that del dot E equals to minus del square E. This one, put this value here 0, you will get del square E comes out to be minus of omega square epsilon into my capital E. Now resolving this two equation number 11, resolve this equation number 11 in the electric field component, that is Ex, Ey and Ez. And for calculating the Ex, resolving this, you will not need to know the del square E. Now see this one, del square E equals to, will be equal to what? As we know that the electric field in the x, y, z direction can be represented as I cap Ex plus me j into me Ey, k into me Ez. Here Ex, electric field, will also be equal to minus of omega square mu into me epsilon I cap Ex plus me j into me Ey plus me k square Ez. I cap, j cap and k cap are the unit vectors. Now on seeing this one Ex and here Ex, on comparing the left hand side and the right hand side, or you can say on comparing the unit vectors in both left hand and right hand side, you will get del square Ex equal to, that comes out to be minus of omega square mu into me epsilon Ex. Similarly this one, and similarly you will get this one. Now similarly we can find out for this equation for magnetic field or the components of Hx magnetic field, Hx Hy, that comes out to be this one. How can we calculate? Now see this one. Here we have taken the curl of equation number 8, and when we have taken the curl of, we will take the curl of this equation, that is equation number 7, del cross H will be equal to what? Minus of j omega del cross E. Now this equation, on solving this equation and putting the, using the equation Maxwell equation number 4, using Maxwell equation number 4, that is this one, that is del dot H will come out to be 0. On using the identity, that is del dot On using the del dot H is equal to 0, that means that is equal to that. Similarly, del cross del square H, that comes out to be minus of j omega mu j omega square mu into my epsilon into my hx. Now on using this equation, similarly I can find out the components of for the magnitude, that is del square hx equal to minus of omega square mu into my epsilon hx, del square hy equal to minus of omega square mu into my epsilon hy, del square hz equal to minus of omega square mu into my epsilon hz. Clear? Now these are the general wave equation, that is equal to del square E, this one, and second general equation will be equal to this one, and one of the parameter, that is del square by del t square equal to minus of omega square. Just put this value on, just putting the minus of omega square equal to del square by del t square, you will get this is another way of representing the generalized wave equation, and this one is the in terms of the magnetic field. Now as we know that the mu into my epsilon is equal to what, mu naught into my mu r, and epsilon equal to epsilon naught into my epsilon r. Mu r is the relative permeability and epsilon r is equal to relative permittivity. Now for the case of air, mu r equal to 1 and epsilon r equal to 1, that is mu naught is the by default value that is equal to 4 pi into 10 to minus 7, epsilon naught equal to 1 upon 36 pi multiplied by 10 to minus 9 farad per meter. On putting this value, mu into my epsilon, that comes out to be equal to this, and that is equal to 1 by c square. So here we will get the mu into my epsilon, that is equal to 1 by c square. So this is the another formula for having the relation, for defining the relationship between the speed of light with respect to the permeability and the permittivity. You will see here that the mu c is equal to under root of 1 upon mu into my epsilon. Clear? Now the wave equation can also be written as, therefore wave equation can also be written as del square E equal to 1 upon c square, this one, and another wave equation can also be in the terms of magnetic field, can also be written as this one, 1 upon c square del square h upon del t square, that is this one is h. Clear? Magnetic field. And this equation is known as the Helmholtz wave equation. The wave propagating through the free space with a velocity of light, that is this equation represents the Helmholtz wave equation. Clear? So this is the basic wave equation for, and in the next next slide we will discuss the main waveguides. And the waveguide we have before the waveguide we have discussed about the wave equation. Now in this we will discuss about the fundamental of waveguide, another one is the parallel plane waveguide, and third one is the rectangular waveguide. Now what are the basics of waveguide? At microwave frequency, the transmission of electromagnetic energy along a transmission line and coaxial cables become difficult due to dielectric losses and conductor losses, that is known as skin effect. Means in the first 5 lectures we have discussed the wave transmitted through a transmission line and coaxial cable, but that is difficult because due to the dielectric losses and the conductor losses, that is also known as the skin effect. So another method for transmitting the microwave signal, that's why we are using the waveguide. A metallic tube, that is waveguide, when we use to transmit the electromagnetic power or electromagnetic signals at the very high frequency, that is microwave frequency. This is another method to transmit, another way to transmit the electromagnetic signal at high macro frequency from one point to the another point, and these waveguides are made from copper, aluminium or brass. Now, what is parallel plane waveguide? The plates which are infinite in one direction, that is y direction, and separated by a distance in x direction, that is this one. If I say this one, this is xy, one plane is there and this one is the another plane, that is known as the parallel plane waveguide. This one, if I say this and this is one plate and this is another plate, and this is known as the parallel plate waveguide. And if I say this one is the x direction, so x direction is finite, and the y direction, if I say this is the y direction, this y direction is infinite. Clear? Now, what are the Maxwell's equation? As we know that del dot D equals to 0, del cross E equal to del minus of del B by del T, del dot B equal to 0, and del cross H equal to J plus min del D by del T. Clear? So, this one is the first Maxwell equation, second Maxwell equation. These are the Gauss law with respect to electric field intensity, and this one is the Gauss law with respect to the magnetic field intensity. Now, what are the longitudinal fields and what are the transverse field? There are two types of field, that is known as the longitudinal fields and the transverse field. If I say the wave let's say this is a waveguide and this one is having an axis z direction, x and y. So, and the wave is propagating in this direction. Now, let's say if I say the field exists which is in parallel to the direction of propagation, that types of field are known as what? Longitudinal fields. Clear? And that means the field which is existing in z direction, that field's components are known as the longitudinal fields. And if I say this is propagation of direction of propagation is z axis, means the electric field exists in the z direction and electric field in the z direction, magnetic field in the z direction. That field components are known as the longitudinal fields. Clear? Now, what are the transverse field? The fields which are perpendicular to the direction of propagation. The field exists which is perpendicular to, let's say if I say this is the direction of propagation, the field exists which is perpendicular to the direction of propagation, it is this one and this one. That means that is in the xy direction. So, that field that are the transverse components, and this transverse component Ex, Ey, Hx and Hy. Clear? So, in the waveguide, I have already told you, in the waveguide, TEM mode does not exist. So, we will discuss why I am saying that TEM wave does not exist. Does not exist in waveguide. Only TE or TM mode will exist in the waveguide, and these components, this transverse component can be represented in terms of the longitudinal fields, that is equal to Hx equal to minus of del H by del H, Hz by del X upon my H square. These equation we will derive for the TE mode for the waveguide in the upcoming slides. So, in the next lecture we will discuss about the transverse fields, and we will find out the components of the transverse field, components of the transverse field in terms of the longitudinal fields. The book I have referred for preparing the slides, that is Microwave Devices and Circuits by SM Liao. Thank you.